2.7 Continental Collisions. Building the Himalayas. The Andean plate meets the Eurasian plate. When a slab of oceanic lithosphere subducts beneath a continental margin, an Andean-type mountain belt develops. If the subducting plate also contains a continent, continued subduction eventually consumes the entire ocean floor and carries the continental block to the trench. Although oceanic lithosphere is relatively dense and readily subducts, continental crust contains significant amounts of low-density materials and is too buoyant to undergo appreciable subduction. Consequently, the arrival of continental lithosphere at the trench results in a collision with the margin of the overlying continental block and an end to subduction. Continental collisions result in the development of mountains that are characterized by shortened and thickened crust. Thicknesses of 50 kilometers or 30 miles are common, and some regions have crustal thicknesses in excess of 70 kilometers or 40 miles. In these settings, crustal thickening is typically achieved through folding and faulting. Noteworthy features of most mountain ranges that result from continental collisions are fold and thrust belts. These mountainous terrains often result from the formation of thick sequences of shallow marine sedimentary rocks, similar to those that make up the passive continental margins of the Atlantic. During a continental collision, these sedimentary rocks are pushed inland, away from the core of the developing mountain belt and over the stable continental interior. In essence, crustal shortening is achieved by displacement along thrust faults, low-angle reverse faults, where once relatively flat-lying strata are stacked one upon another. During this displacement, material caught between the thrust faults is often folded, thereby forming the other major structure of a fold and thrust belt. Excellent examples of fold and thrust belts are in the Appalachian Valley and Ridge Province, the Canadian Rockies, the lesser southern Himalayas, and the Northern Alps. The zone where two continents collide is called the suture. This portion of the mountain often preserves slivers of the oceanic lithosphere that were entrapped between the colliding plates. As a result of their unique ophiolite structure, these pieces of oceanic lithosphere help identify the location of the collision boundary. It is a long suture zone that continents are described as being weld together. We will take a closer look at two examples of collision mountains, the Himalayas and the Appalachians. The Himalayas are the youngest collision mountains on Earth and are still rising. The Appalachians are a much older mountain belt in which active mountain building ceased about 250 million years ago. The mountain building episode that created the Himalayas began roughly 45 million years ago, when India began to collide with Asia. Prior to the breakup of Pangaea, India was a part of Gondwana in the southern hemisphere. Upon splitting from that continent, India moved rapidly, geologically speaking, a few thousand kilometers in a northward direction. The subduction zone that facilitated India's northward migration was located near the southern margin of Asia. Continuing subduction along Asia's margin created an Andean-type plate margin that contained a well-developed volcanic arc and accretionary wedge. India's northern margin, on the other hand, was a passive continental margin consisting of a thick platform of shallow water sediments and sedimentary rock. Although the details remain somewhat sketchy, one or perhaps more small continental fragments were positioned on the subducting plate somewhere between India and Asia. During the closing of the intervening ocean basin, a relatively small crustal fragment, which now forms southern Tibet, reached the trench. This event was followed by the docking of India itself. The tectonic forces involved in the collision of India with Asia were immense and caused the more deformable materials located on the seaward edges of these land masses to be highly folded and faulted. The shortening and thickening of the crust elevated great quantities of crustal material, thereby generating the spectacular Himalayan mountains. In addition to uplift, crustal shortening produced a thick mass of material in which the lower layers experienced elevated temperatures and pressures. Partial melting within the deepest and most deformed region of the developing mountain belt produced plutons that intruded and further deformed the overlying rocks. It is in such environments that the metamorphic and igneous core of compressional mountains are generated. The formation of the Himalayas was followed by a period of uplift that raised the Tibetan Plateau. Evidence from seismic studies suggests that a portion of the Indian subcontinent was thrust beneath Tibet, a distance of perhaps 400 kilometers. If so, the added crustal thickness would account for the lofty landscape of southern Tibet, which has an average elevation higher than Mount Whitney, the highest point in the contiguous United States. Other researchers disagree with this scenario. Instead, they suggest that extensive thrust faulting and folding within the upper crust, as well as uniform ductile deformation of the lower crust and underlying lithospheric mantle, produced the great crustal thickness that accounts for the extremely high plateau. Further research is necessary to resolve this issue. The collision with Asia slowed but did not stop the northern migration of India, which has since penetrated at least 2,000 kilometers or 1,200 miles into the mainland of Asia. Some of this motion can be accounted for by crustal shortening. Much of the remaining penetration into Asia is thought to have resulted in the lateral displacement of large blocks of the Asian crust by a mechanism described as Continental Escape. As India collided with Asia, parts of Asia were squeezed eastward out of the collision zone. These displaced crustal blocks included much of present-day Indochina and sections of mainland China. Why has the interior of Asia deformed to such a large degree, while India proper has remained essentially undisturbed? The answer lies in the nature of these diverse crustal blocks. Much of India is a shield, composed mainly of crystalline Precambrian rocks. This thick, cold slab of crustal material has been intact for more than 2 billion years. By contrast, Southeast Asia was assembled from, more recently, several smaller crustal fragments, during and even after the formation of Pangaea. Consequently, it is still relatively warm and weak from recent periods of mountain building. The deformation of Asia has been recreated in the laboratory with a rigid block representing India pushed into a mass of deformable modeling clay. India continues to be thrust into Asia at an estimated rate of a few centimeters each year.